As an artist and researcher at Media Art Exploration, I've been investigating the political assumptions that underpin machine learning. Machine learning is celebrated for this novel approach to teaching machines to think more like humans. They're trained on massive amounts of data until a neural network is able to produce an accurate prediction for a specific task. Everything in machine learning boils down to optimization, to tuning the system to achieve better and better results over time. A neural network's overall efficiency is evaluated based on its accuracy as well as its size and speed. The leaner the network, the better. But what is lost then in this optimization? Practicality may necessitate boiling down a map to its features most important for navigators, but we must consider what is lost in this minimization process. What do these navigators think is important? And what does it say about our relationship to accuracy that we place it second to optimization? I will take a very basic problem as the target for machine learning, adding two numbers together. This is something long solved by computer scientists. Arguably one of the most fundamental aspects of computing is the ability to add numbers together. But rather than rely on the established method, what if we abstracted this process to machine learning? Machine learning utilizes something called a neural network. In the case of adding two numbers together, there are two inputs to this network, the two numbers we're trying to add together, and one output, the sum of those two numbers that we are adding together. Between the inputs and outputs is an arbitrary number of neurons connected in succession, each passing along signals down the chain in the way neurons in our brain pass information down the chain. The system flows left to right, going from the inputs, passed through the various hidden layers of neurons, this black box, and eventually flows out the output as a prediction or a value of some kind. In this case, hopefully, the sum of those two numbers. You can think of a neural network as a river. It flows in one direction, and in it there are various obstructions that determine how it bends and how the water moves. There might be fallen trees or rocks or leaves in the water that serve to contribute to the overall direction of the water. Using the river analogy, we might say that when the river began, the things were very chaotically laid out. The rocks and the trees were causing the river to have a very turbulent flow. But over time, things got kind of pushed aside and maybe it settled into a natural position and the river became a steady flow with a predictable output. The training process of a neural network is to take thousands and thousands of predictions from the network, look at those predictions, determine how wrong they were, and then adjust the neurons in the network accordingly. Using the river analogy again, we could say, we know we want the river to look like this. We want the water to flow like this. And so where would we place those various obstructions along the way in order to get that particular flow from the river? What you want to do is over time make very small adjustments that nudge the river into the right direction to give it the right flow that you want. This river metaphor might be a bit spurious as applied to machine learning, so I'm going to call my friend Francis Tseng to see if he can give us a more technical overview of what's going on. Hey, I've been using this river analogy to explain machine learning, and I thought maybe you could give us a more technical overview of this stuff, like weights and biases and backpropagation.
Yeah, weights and biases are what are called the parameters of the neural network. So they basically define what output it gives. So a good neural network for whatever task you're training it for will have weights that give you like the correct output, like if this image is a cat or a dog, whereas the incorrect weights will give you a random answer. So that's kind of what you're changing, you're tuning to get a good model. Your question might be like, well, how do you find the right weights? Backpropagation is basically the method that lets you do that. And the way it works is you have some kind of sense of what a correct answer is. At the beginning, the neural network is going to be like wrong or way off or something like that, but you can tell how wrong it is. And backpropagation basically lets you slowly make adjustments so that it's less wrong each step of training. And eventually you get that wrongness or whatever to be as low as possible.
Awesome, thank you.
The process of backpropagation relies on vast sums of data to be fed into the network as examples from which to learn. For some machine learning tasks, this could mean feeding in hundreds of thousands of images of human faces, or in the case of adding two numbers together, the data is simply thousands of pairs of numbers and their respective sums. Given enough data, the network will have enough examples from which to direct its flow of information accordingly, resulting in a well-trained neural network. Adding two numbers together. You could simply imagine the training data as a spreadsheet with three columns. Column A plus column B equals column C. This is where the optimization problem is located. In this example, the network takes a data set with tens of thousands of numbers, often data sets are much larger, and reduces it to a series of 23 interconnected neurons. In this case, I've decided to run the network for 10 epochs, which is to say that it will go through the training data in its entirety exactly 10 times. Now that we have some idea of how the network performs, I'll give it two numbers to add together. Let's try 1 plus 2. Okay, and 5 plus 8. How about 5,000 plus 4,326?